Welcome to this BOXERMesh demonstration. In this short video, I'm going to show you how to use BOXERMesh to produce a mesh for a cool turbine blade geometry. The first step is to import the geometry. BOXERMesh can directly import a wide range of CAD formats. Here we're using an STL tessellated geometry, which we'll select and open. You can see we have a cool turbine blade for use in a wind tunnel cascade. We can view the geometry, and we can turn off patches by clicking in the feature tree. And you can see the internal passages in this blade and cooling holes on the blade surface. A micro selection option allows you to hide individual facets. We can cut the geometry and look inside. Let's turn the geometry back on and we'll deselect the discs on the top and bottom of the blade to get a better view. Moving to the mesh setup phase, the first thing we do is set a bounding box, which defines the extent of the meshing domain. Here we'll use a Cartesian domain with a fixed width in the y direction. We can enter the coordinates here by hand because we know their dimensions. You can also point and click in the GUI. We'll set 20 cells in the y direction, and this sets the background reference length scale. We can preview this, and you can see we're just meshing a thin slice of the blade. You can change the Z limits to capture the full blade height. The next step in the setup process is to define a fluid region by marking a cell with a seed point that lies distinctly in the fluid region of the mesh. We enter the coordinates by hand and we can preview the location of this point. Here you can also enter the seed point location using point and click in the GUI. Having set up the domain, we now define the mesh sizes on the geometry, and we can do this by patch name. BOXERMesh's octree approach refines the mesh by subdividing background cells. Our background length scale is defined by the bounding box at level 0. We select level 3, which is 3 subdivisions of the background cells, and we drag and drop the blade surface patch from the feature tree. The same is done for the other patches at different refinement levels. BOXERMesh has a very useful quick preview function, which displays cubes on the geometry that correspond to the current mesh specification. Here you can see cubes on the blade surface, the leading edge, and the holes, all at different refinement levels. We can click off the geometry and see the passages, and also the ribs. And that looks about right in terms of the refinement level for the geometry. These preview cubes allow you to see whether the requested sizes are appropriate for the geometry and application before you even start meshing. The final step in the process is to specify near-wall layer mesh parameters. We add a layer specifier, we set the total number of layers to 6 with a fixed first cell height and an expansion ratio. We can drag and drop patches from the feature tree to apply the specifier to those patches. Now the setup's complete and we're ready to mesh. BOXERMesh produces a hybrid mesh via an octree, so let's click here to generate the octree. We can go straight to a hybrid mesh in one click, but there's a benefit to generating the octree first. And you can see that was very fast, less than 10 seconds. The octree mesh is a hanging node, castellated mesh that sits off the geometry. A big benefit of generating the octree first is that you can check that the mesh resolution is correct, and you get a very fast representation of what your final mesh might look like. We can now generate the hybrid mesh, and we'll click here to start this process off. The hybrid meshing process removes the hanging nodes, morphs the octree surface down to the geometry to get a fully conformal body-fitted mesh, and grows viscous layers. I've sped this section of the video up, but we'll see the total elapsed time when it's complete. While it's running, I'll briefly mention some of BOXERMesh's other features. BOXERMesh was written from the ground up as an MPI parallel program to tackle large and complex real-world geometries. Our octree approach makes it tolerant of poor quality CAD, and another big time saving is that the mesh produced is ready to run, and you don't have to spend time fixing a handful of problem cells. With BOXERMesh you can mesh intricate objects like cool turbine blades significantly faster and much more reliably and predictably than using a regular meshing process. That's completed in about 2 minutes, so let's take a look at the mesh. Turning the octree off, you can see the body-fitted conformal mesh with tri and quad elements on the surface and no hanging nodes. The holes are well resolved, and the edges are sharply captured, and this happens automatically, without user input. Inserting an isosurface through the volume mesh shows you the grid structure. You can see the internal passages have been fully meshed. BOXERMesh has flood-filled the domain from the seed point that we specified earlier. Zooming in on the leading edge, you can see it has a high-quality layer mesh around it, and this continues along the whole blade surface and also at the trailing edge. BOXERMesh is easy to learn and straightforward to use. It has produced a mesh on this complex geometry with only a handful of simple operations. This gives you a good idea of what it's capable of and how it might be able to transform your meshing process and enhance your productivity. Visit us today at www.cambridgeflowsolutions.com.